Hi, welcome back. Today we're going to talk about some calculus on polar functions. But before we do that, I'm going to introduce this idea that relates our polar equations back to parametric equations in Cartesian land. So you'll remember that we have a way to convert between uh, polar coordinates and Cartesian coordinates. And that is that uh, if you have a point that is written as r theta, then we can get an equation for what the x coordinate is and the y coordinate is by writing x is equal to r cosine of theta and y is equal to r sine of theta. Now, what this means is that if we actually have a function like r is equal to f of theta, and so this is a polar function. This is over in polar land where you give me an angle and I'll tell you how far out on the radius to draw the point. Then we can take this idea and connect it with our conversions and see that when you have a polar equation that looks like r is equal to f of theta, then what we can do is we can write it as x of theta and y of theta, where we replace the r by f of theta. So x of theta is equal to f of theta cosine of theta. Y of theta is equal to f of theta sine of theta. And if you look at that, what you actually have is you have a set of parametric equations. And if you wanted to feel more comfortable, you could write this as x of t is equal to f of t cosine of t, and y of t is equal to f of t times sine of t. But in any case, it's exactly the same thing, just with this variable t representing the angle theta that you're passing through. And so this is a nice way to convert between an equation that's written in polar form into some parametric equations. And so a number of the techniques, of the ideas from parametric equations can be brought over to polar equations in that way. So in particular, what we're going to work on right now is we're going to talk about the slope of the tangent line to a polar equation. And so we'll do a quick digression over to how this works in parametric land, and then we'll talk about it in polar land. So let's say that we have a parametric function, x of t, or x equals f of t, y equals g of t. And so we've got this function going around, this curve going around when we're plotting it, and we're at some point here on the curve, and what we'd like to know is we'd like to know the slope of the tangent line to this curve. So what we had done in the past is we had looked at this as a vector function, and for a vector function, we know that we can take the derivative of it, and we get the vector in that direction. So that's one way to approach this. Another way to approach this is to use a little bit of chain rule. So if we think of y as a function of x implicitly, then what we really care about is we really care about the derivative dy dx. But what we can do is we can say, well, what happens if we take the derivative of y with respect to t? Well, the derivative of y with respect to t is the derivative of y with respect to x times the derivative of x with respect to t. So the slope of the tangent line is going to be dy dx is equal to dy dt divided by dx dt, provided that dx dt is not zero. And if both dx dt and dy dt are 0, remember that's meaning that the point has stopped. And so at that point, we would say there's no actual slope there. So if dx dt is not equal to 0, and so what we have is we have that this is a way to calculate the slope of the tangent line to any parametric curve. Now we can do the same thing here in polar land, where we can say, oh, if we wanted to calculate dy d theta, and so here let's write our polar equation r equals f of theta as in parametric form, x of t, x is equal to f of theta times cosine of theta, y is equal to f of theta sine of theta. And again, we can apply this idea of the chain rule to say that dy d theta is equal to dy dx times dx d theta, and get that dy dx is equal to dy d theta divided by dx d theta if dx dt is not equal to 0. Now, we have that x and y are more complicated functions of theta, so we'll have to take these and plug them in, and then we'll get a more general form, a form that we can apply when we have an r cosine of theta and an r sine of theta here. So let's do that. So dy d theta, if dy d theta is equal to the derivative of a product of two things, so the derivative of the first, so dr d theta times the second, plus the first times the derivative of the second, cosine of theta, and dx d theta is the derivative of the first times the second, plus the second, plus the first times the derivative of the second, negative sine of theta. And so you get this rather complicated looking expression for the slope of the tangent line. Slope of the tangent line is therefore dy dx equals dr d theta sine of theta plus r cosine of theta over dr d theta cosine of theta minus r sine of theta if this is non-zero. All right, so that's how you can calculate the slope of the tangent line using when you have a function that is in polar coordinates. We'll do some more calculus in a little bit. See you soon.